She went to Colorado College. Was Ag Associate at the same time?
Yeah, we
So
were in the
yeah,
same class. Sorry?
you guys were in the same class?
Yeah.
Oh, that's too funny.
It was fun, yeah. It was a good time.
I haven't chatted with them in ages.
He was in San Francisco now.
Oh, okay. I know a lot of those people from high school. I talked with.
Sure.
Yeah, my friend group kind of part of it, because most of them went back to Europe because their family.
Oh, yeah.
So,
We friends with like Inez and.
Inez, Natalie, Amanda. Yeah.
Oh, yeah. I keep up with Leo at work because we were in lacrosse together. He's doing like pilot school. I think he's.
Okay. Last time, was what? I finished up linear and we did separable. Today's exact. This is where you need Calc 3. So it's going to be of the form m of xy dx plus m of xy dy. That's a differential expression. The equation will generally then equal 0, will have to equal 0. Right, so that expression is an exact differential in a region R if it corresponds to some function big F of xy defined in R. This is where the vectors can come in handy. That big F is called the potential function. So if you just think of mxy and xy as a vector field, right? M is your first component, n is your second component. Then if that vector field is conservative, the differential is exact. And your big F is your potential function. This is the test for it. Partial n partial y equals partial n partial x. That is both the test for conservative, the vector field is conservative, and also for it being an exact differential. Method of solution, again, you can just read through that all on your own. I'm just kind of copying these from the notes I have written. Just makes it easier than trying to write up a bunch of slides. Here's the actual method. First thing you want to do is verify it's exact. Right, so now that is 3 types of equations if you're given an equation to choose from. Is it linear, is it separable, or is it exact? If it is exact, you want to find your potential function. You've taken Calc 3, you've done conservative vector fields, find the potential function. You know that this isn't a strict process. You can either do the partial with respect to x first or with respect to y first and integrate. If you're not familiar with it, you're probably going to wind up following this procedure step by step. You set partial f partial x equal to big M and integrate with respect to x. That will give you some antiderivative plus a function strictly of y. Because you take the partial of a function only of y with respect to x, it's 0. It's treated as a constant. Then your goal is to find that g of y. So you take the partial now with respect to y, set it equal to n, solve for g prime, integrate to get g, and that is your potential function. Potential functions are a family of functions because there is going to still be that constant of integration out of g prime, right? But we'll take the simple one where it's 0 because we're just going to wind up moving it to the other side, so equal to sigma. Which means even this technically isn't anything new. This is just Calc 3, finding potential functions. Again, why Calc 3 is not a prerequisite? I don't know. But here we are. Just decided by people who make more money than me, so they're smarter. Actually, I'm not sure if the curriculum is actually decided by the department itself. I believe for all of these, we're going to determine if it's exact and solve only those that are. Now, there is a way to make certain equations exact using an integrating factor, a different integrating factor than for linear. That is covered in section 2.4, I believe, which is part of the substitution stuff. I don't think I cover it in class, so you'll need to read through that section, but it's not that difficult. But then the idea is the same. You find your integrating factor, you multiply through by that integrating factor, and it makes the whole thing exact, and then you solve it using that method. We're not going to worry about that for this. If it's not exact, we're not going to try and make it exact. It's not exact. Determine if it's exact. First thing you want to do, I'm not going to do this for every problem. Write out your M and your N. You need to identify your M function. And that is the function attached to the X differential. So it may not always be written in that order. Right? So you have to look for where is dx, what's the function attached to it, that is n. And n is just the function that's attached to the y differential. Now apply the test in theorem 1. Those are called the mixed partials. Partial n, partial x. So for this purpose, who are my calc 3 people? Who've had calc 3? Excellent. One of you, what's partial n, partial x? How'd you get it?
You get the partial, just integrate x squared of the n function.
Integrate?
Yeah. Derive.
Differentiate.
Differentiate. Alright.
So what happened to the 1?
Turns to 0.
Right? And what if that was a y instead? What if that was y plus x squared? What would the partial with respect to x be? Same thing, y. When you take the partial, you treat all other variables as constant. And I'm going to pick on someone. Joe.
Yeah.
Partial n, partial y.
Partial m, partial y. So we take with respect to x, or with respect
With
to y.
respect to y, yes.
Yeah.
What is that derivative? Or not derivative, it's not really a derivative. What's that partial?
Oh, it's going to be two.
Just 2?
Yeah. Two x.
2x.
No.
It's with respect to y.
Right, but then if we're treating it as a constant.
Right, so your 2x is your coefficient.
Okay.
It would be 2y if it was with respect to x. Right, because then your 2y would be your scalar multiple. I'll give you 70 because you eventually got there.
All right, thanks. Appreciate it.
And
I'll take it.
it's one of the downsides of having me for multiple classes didn't get picked on a lot. Especially when you decide that my class wasn't important enough to show up for on Tuesday.
So this might be a stupid question. So when it's dndx.
Okay, so be careful.
Over dx.
That's not D,
Okay,
that's a partial.
okay. So I guess,
That's D.
okay,
And it is that actually that distinction is important in study in calculus, right? Because these are not technically differentials. They're partials,
okay,
right? You can't really differentiate a multivariate function.
okay.
You can find the differential. Remember, like you have dy equals f prime of x dx. That's the differential for y. So you could find the total differential for z dz,
Mhm.
but you can't actually find dz dx. That doesn't exist. That's why we use partials.
So I guess when you're solving a partial, is it just the derivative of the one that would be?
No, so you differentiate the exact same way,
Okay.
except you treat all other variables like they're a constant.
Gotcha.
Right, so in this case here,
Mhm.
because it's with respect to y, you treat x like a constant, so treat it like 1. So this is like 2 times 1 times y. Now it's d dy of that,
Gotcha.
2 times 1.
Yeah, yeah,
But we said the 1 was x, so it's 2 times x.
gotcha,
That's how the partials work.
gotcha.
So it's the same as calc 1, except to hold other variables constant.
Okay.
Does that make sense?
Yeah, I think it's just weird because it's a new concept. But,
Again,
get used to it.
The calculus should be a requirement for this course. Here we are. So you'll have a head start when you get to this in calculus. So this symbol here is called the del symbol. And again, for those of you who've had Calc 3 or E&M, that's not to be confused with the del operator. That symbol is nabla. But a lot of times when we're talking about, again, for those who are familiar with it, curl, we'll say like del cross f. We actually mean nabla cross f. We call it del because it's actually the del operator. Don't know why they came up with that terminology, but they did. So once again, here we are. And then of course you have del squared, which is the Laplacian, which is also pretty cool. We'll study that in calculus. Are they the same? This is exact. Which means there exists a function big F, where the partial of big F with respect to x, so that's another notation for partials, the subscripts, equals m. The partial of f with respect to y equals n. And that is a solution to our equation, which means our goal is to find that big F. We were just talking about this before class too, all the shorthand symbols. So I'm just rewriting it, right? Big F, the partial of f with respect to x is 2xy. Partial of f with respect to y is 1 plus x squared. Our function, right? So the method itself says to integrate the partial with respect to x. It doesn't matter. You could do either one. I'm actually going to stick with that because that does seem to be the easier one for my purposes. And what is that antiderivative?
X squared y plus g prime of x.
Not g prime. Plus just some function of y. I use f. I'll use as y. Or the source that I got my notes from uses g. Doesn't matter, it's just a function. Now take that partial with respect to y. X squared y, what is that partial with respect to y? It's just x squared. Take a function strictly of y. What is its partial with respect to y?
F prime.
It's just the derivative with respect to y. But that has to equal 1 plus x squared. Which means that f prime has to be 1. That means that f of y has to be the antiderivative of 1 with respect to y. Which is just what? Y plus some arbitrary constant, we can ignore that. For this application, we can ignore now that constant of integration. And there is your solution. For this one, we can actually find an explicit solution, can't we? So you can factor out the y and say that y of x equals c divided by 1 plus x squared. That's our solution. That's all there is to solving the exact equation.
Can we leave it in either form, or do you want it as well?
Generally speaking, if possible, always write it in an explicit form. It's just a general rule of thumb. But for right now, I don't care. I'm just worried, can you actually use the method to get a solution? Unless it says, write it in explicit form. Maybe I'll do this one last one, and I won't write out N and N. Identify n. Just y. You don't need the differential in with it. Identify n negative x. What is the partial of n with respect to x? Partial of n with respect to y. What is it? Are they the same? This is not exact. And for now, that's where we're going to stop. Like, so I'm not actually going to write out m and n this time. What are we going to want to take the partial with respect to x of? Process of elimination would be one. Remember, that's why we call it mixed partials. Right, your n was x cosine of y minus 2y. Right, so you take the partial with respect to x of the term attached to the y differential. What is that partial? Just cosine of y. We want the partial with respect to y of the term attached to the x differential. What is that partial? Are they the same? Right, that means that there's going to be a function whose partial with respect to x is x plus sine of y, and its partial with respect to y is x cosine of y minus 2y. Our goal is to find that function. To find the antiderivative of x plus sine of y with respect to x. What is its antiderivative?
y plus 2y.
Plus some function of y. Now take that partial with respect to y, what do you get?
Cosine y f prime y.
That has to equal x cosine of y minus 2y. Which means that prime is negative 2y. What's f?
Negative y squared.
Minus 1 squared. That would be our solution. Or get rid of fractions. Can that be explicitly solved for y? Nope. So leave it. We need to determine if this is exact. The very astute should be able to see what m and n are from this. But if not, we need to write it in proper form. What's another way of writing y prime?
Dy over 0. But that's the format we're most used to. Right, so there we go.
what do we want partial x of?
Two y minus x. Two x y.
Go ahead and take that partial with respect to x. What do you get?
Negative x squared e to the xy minus e to the xy.
I agree with the negative e to the xy. How'd you get the x squared?
I did first times derivative of the second times derivative of the first. So I used chain rule e to the xy.
What's the partial of xy with respect to x?
Or y. So it would be negative x y e to the xy minus e to the x.
And what are we taking the partial with respect to y of?
Plus y x y.
Negative 2 minus 1.
Two ways you could write it. That way, or negative the quantity of what you said. And so remember, it has to be of the form m dx plus n dy. Right, the signs in both of them are positive, or pluses. And what is that partial?
Minus yx xy.
Are they the same?
Yeah.
That means this is exact. And so we have to have both of these. I think I'm going to do it with respect to y first. Just because there's less negatives in it. What is that antiderivative? I'll do the hard one for you. You're welcome. What is the antiderivative of x e to the xy with respect to y?
Just gonna be xy e to the xy.
What is it?
Xy e to the xy.
That's partial with respect to x. I want antiderivative. So what function, when you take its partial with respect to y, gives you x e to the xy? That's what it's asking.
X, Y, E, 4.
E to the xy.
Just e to the xy. Two ways to approach it. The way that I just mentioned, just think, okay, what function, when you take its partial with respect to y, gives you x e to the xy? You should easily see that's e to the xy. You could also do change of variable. Let u be xy. Now what's the differential for that? X dy, right? You have your x dy. Be careful with that though. If that x wasn't there, you wouldn't be able to use u sub. Right, or let's say that was e to the x squared y, and you tried to do u sub. You'd be left with 1 over x, right? You need to multiply by 1 over x, but you're not allowed to do. That requires Jacobians. That's a different change of variable. So just be careful when you use change of variable in multivariate anti-differentiation. And we're left with just some function of x. Now take that partial with respect to x, what do you get?
Partial with respect to x?
Yes.
Sorry.
E to the xy times y plus f prime.
And that has to equal the -2 minus y e to the xy. Well, that means our f prime is just -2, right? And so f would be -2x. Y squared minus 2x minus e to the xy equals some constancy. That is our solution. And again, that cannot be solved explicitly for y. Also can't be solved explicitly for x, by the way. Which actually does bring up a good point. In this one, we knew that the dependent was y. We actually didn't know that for any of the other ones. And we're not really told what our dependent is. We were just assuming y. So, assuming y, I could solve this explicitly. Could I have solved that explicitly for x? If x was the dependent. No. Why?
X squared.
X squared.
So you couldn't do the plus or minus square root.
That's not an explicit solution. That gives you two possible solutions. If we add a restriction, x is either non-negative or non-positive, then yes, you could find an explicit. But with the given information, you can't. Which is why I generally probably just leave it in the implicit form unless I tell you what the dependent is. And so decide whether this is exact. So we need to do two partials. Partial with respect to what? Two variables. What is it?
Y and t.
Let's do y first. Doesn't matter. What are we going to differentiate with respect to y? Which equals what? Y. Oof, that was really tough. Now we need to do partial t. Of what? What's that partial? Is this exact?
Yes.
Switch up. Don't use big F this time. For this one, let me actually use one that's I'm more comfortable with using. Capital B. That's what we use in physics for the potential function. But again, it doesn't matter, right? It's just a function variable. V sub y has to equal two yt plus 1. And the partial with respect to t has to equal y squared. Now that y squared is definitely the easier one to anti-differentiate, right? What is that antiderivative?
Y squared t. Plus,
Plus what?
or sorry, 1.
Function of t,
Function of what?
t, or is it y?
This one, y. Right, you're anti-differentiate with respect to t, so the function's gonna be with respect to y. Now we take that with respect to y, which is what?
Two yt at prime y.
That's equal to 2yt plus 1. That means f prime of y is what? Just 1? F would just be y. Y squared t plus y is equal to 6. Under the safe assumption that y is the dependent and t is independent, that has no explicit solution. T would have an explicit solution. I'm just going to leave it like that. What do you want partial t of?
Two x squared t, 2x cubed. And d to the dx.
Right, so now the question is, why is it not 2x squared t minus 2x cubed?
Because there's more instances of t.
And what are we looking for? Mixed partials. So with respect to t,
Oh, you wouldn't take it of dt.
you want the one that's attached to the dx.
Yeah.
That would be the mixed partials. What's that partial?
Is 6x squared plus 4xt.
Now we want partial x, process of elimination. What's that partial?
4x minus 6x squared.
Is this exact? Now we need to find the potential function. Right? For this one, I'm going to use the other commonly used symbol for potential functions. This is, I guess, a good extra credit type question. Maybe remember it. It's my favorite Greek letter. Sigh. There are any points if you can tell me why that's my favorite Greek letter. I actually don't know if you would know this. I don't know if I mentioned it before.
That was 3 years ago, or 2 years ago, so.
Doesn't matter.
Even if you did tell me.
It doesn't matter, I'm your favorite instructor, so you have to remember everything about it. But I don't think I ever mentioned it before.
Pitchfork shape? Okay.
So it's definitely pitchfork shape, that's not why.
Oh, okay.
My friend called it I think it was the devil's trial, not the devil's pitchfork,
Okay.
because of where it comes from. Schrodinger's equation in quantum mechanics. Use the psi. So I work with it a lot. Psi of t would have to be 2x squared t minus 2x cubed. And then we want psi with respect to x. So that's lowercase psi. That's capital psi. Capital psi is used in quantum. Lowercase psi is used as the potential. And I think psi is actually a vector too. If I remember correctly. I think it's a vector too. And psi of x would have to be that 4x cubed minus 6x squared t plus 2xt squared. Which one would be easier to start with? Probably the one with respect to t. I don't think it matters. What's that antiderivative?
X squared t squared minus 2x cubed t plus psi of x.
Well, not psi.
Or
So some function of x, and you always want to use a different representation in this case, right? If you said that was psi, that's implying that's the potential function. So that's what we're using. So just use something different. We now have that partial with respect to x. What is it? What is it?
2x t squared minus 6x squared t plus f prime of x.
And that has to equal that, right? That means that f prime of x is 4x cubed. What's f?
Plus 4 plus c.
And we just ignore that c. And that would be our solution. Which unfortunately cannot be solved for explicitly. For either one, by the way. So that's the idea behind exact equations and solving them. Any questions on that? more than 30 minutes. I think it's 40 minutes. 10-minute break at 2:50, we'll move on, we'll look at substitutions. So looking at miscellaneous substitutions. First substitution we deal with is for an equation that involves a homogeneous function. All right, so this is the definition of homogeneous functions. Function will be homogeneous if it satisfies the property f of tx ty equals t to some power times f of xy. Right, call that power alpha, then it's homogeneous degree alpha. Differential equation in differential form is homogeneous if both of your functions m and n are homogeneous of the same degree. Right, then you'd be able to use one of these two substitutions. If I remember correctly, that will make it separable. Using one of those two substitutions should make it separable. Maybe linear. Right, and then I think this is all kind of going over the method. So again, read that at your leisure. Then we also have what's known as a Bernoulli equation, which is an equation of the form dy dx equals p of x times y plus q of x times y to the n. Right, if n is 0 or 1, clearly it's linear. For any other value, you're just going to use the substitution u equals y to the 1 minus n. And I believe that will make it linear, if I remember correctly. Yes, it makes it linear in u. And like I said, read section 2.4. I think it's 2.4. That's integrating factors for exactness. That can make an equation exact, which I'm going to cover with these substitutions and with miscellaneous techniques. Show homogeneous and then solve. Again, remember y prime same as dy dx. So we can get in this form. Again, I'm going to, in this case, actually, I will always write it out. I'm going to identify capital N. I'll write it as x plus y. And the capital N. I'm going to show that they are both homogeneous of the same degree. It shouldn't be difficult just looking at that to see that clearly they're going to be homogeneous degree 1. But I'll show it. That's what we're going to evaluate. That's how you chose homogeneous. Degree 1 in this case, right? N is just stupidly trivial. I forgot the negative. Oops. So what we say, English, right? ELS. So both are homogeneous degree 1, which means the equation is homogeneous. Not to be confused with a homogeneous linear differential equation. That's something different. This allows us to use one of two substitutions, right? Either u equals y over x or v equals x over y. Which means y would be u times x, or x would be v times y. Doesn't matter. Custom is to replace the y. So I'll use y equals u times x. We now want y prime. What's y prime?
It's gonna be 1.
You made a fatal flaw. You assumed u was constant.
chain.
Product
Product.
rule with chain rule, yes. Because u is not constant, it is variable with respect to x. So it's x u prime plus u.
So there's no x prime?
What's x prime? What's dx dx?
1, okay.
Then what we get, go back to the differential equation and make the appropriate substitutions. That was y prime equals y plus x over x, so we have to replace y. We're gonna be left with just u plus 1, right? As long as x is not 0. Those two are not actually equal, are they? And so this statement is actually not a tautology. That statement is false. Now it's true. Now what we'll do. Not right. Subtract u from those sides. U prime is 1 over x. U would just be the antiderivative then, right? What's that antiderivative? That's u. But we didn't want a solution for u. We want a solution for y. Actually, we don't know if we want a solution for y. I'm assuming it's y. It is y, that's right. We do know because I said y prime equals. What's u? What does u equal?
Y over x.
Y over x. And there's a solution, which can be simplified. You don't have to do that. That would be our solution. That's using the substitution. So every time, if you're going to use a substitution, you're going to get one of linear, separable, or exact after you make the substitution. So it's not really a new technique. It's a technique to get it into one of those three forms and then solve. show homogeneous and then solve. And again, generally speaking, you should be able to look at the equation and determine if it's homogeneous or not, just from looking at it. May take you a little bit of time to start seeing it, but with enough practice, you should be able to see it. What is M?
Two y to the fourth plus x to the fourth.
What is N?
XY cubed.
Negative.
Negative xy cubed.
Oh, because, yeah.
It's minus.
Okay.
Right. Now we evaluate. That'll give us 2 times ty to the fourth plus tx to the fourth. Factor out the t to the fourth, are you left with n? Homogeneous with degree 4. Negative tx times t cubed y cubed. What does that simplify to?
Negative t to the fourth xy cubed.
Gives you t to the fourth n. N is also homogeneous of degree 4, so the whole thing's homogeneous. Nice. Equation is homogeneous. All right, then we use that substitution, y equals u times x. Always leads to y prime equals xu prime plus u. Now make the required substitutions. And it was what, 2y to the fourth plus x to the fourth? Xy cubed, right? Simplify that. X to the fourth comes out, right? Two u to the fourth plus 1 over u to the fourth for x not equal to 0. Sorry, not u to the fourth, it should be u cubed, right? That can still be simplified, though, can't it? That's what, 2u plus u to the minus 3? X u prime winds up being that, right? Now, let's put that back as a single fraction. You should be able to see how this separates. U cubed over u to the fourth plus 1 du is equal to dx over x. Which means those antiderivatives have to be equal, right? Look at the left-hand one. What is that left-hand antiderivative? How would you evaluate it? I'm not going to call it u sub in this case, but yeah. Change a variable. W sub. Not u because we're already using u. What's the derivative of u to the fourth plus 1? Four u cubed, right? We have a u cubed du. We don't have a 4, so we're going to multiply the result by 4. Notice I'm not using absolute values. U to the fourth plus 1 is always positive. So I don't need it. Upload pending. multiply by 4. I'm going to use laws of logs to say that's going to be log of x to the 4th, right? And unfortunately, that's sad. So we'll just pick up here Tuesday. We'll finish up substitutions on Tuesday. And I think after that is starting models, starting some first order models. 3 types in particular I focused on in the book. It's exponential growth and decay. So we're actually finally able to derive the exponential growth model. I then think it's Newton's law of cooling and mixing, that's section 4.2. And 4.3 is my favorite, elementary mechanics, which is physics, which is unfortunately a reminder of my classical mechanics class. And yes, that does mean that we're not going to ignore friction all the time. We will actually examine no longer free fall, but a body that's falling and include drag, air resistance. We're going to then solve those types of problems. That's going to be the heavy focus on motion. What? 25 minutes. Something like that. I think the first exam's going to be
The 24th, right?
something like that. So we're getting close. But that's the goal. Have a good weekend.